Okay, we're going to pick up here, finish up 15 and then roll into 16, I think. So last time we really got into really titrations, and obviously you did some titrations last time. And we talked about really solution stoichiometry. And as we talked about, really the good news is it's sort of the same steps along the way. Again, you want to make sure always in stoichiometry you got a balanced equation. You want to make sure that you convert to moles. You also want to make sure, right, you check whether or not it is a limiting reagent type of problem. You want to again add right and go 3 next. You want to then do the mole to mole relationship. And lastly, obviously take those moles to some other unit. As we talked about last time, typically titration problems, solution stoichiometry problems, it's really, again, kind of steps 2 and really steps 4 here that are usually different than a basic stoichiometry problem, which is instead of grams per moles to get our moles or to convert those guys using the molar mass. We do oftentimes we use molarity. And again, here, if you use it sort of up front, you usually would be solving for moles, which would be liters times the molarity. Also, at the end, as we saw in a couple of examples, there's kind of 2 endings sometimes that will also use the molarity sort of equation. Sometimes you may actually just be looking to calculate the molarity, and you would use the moles from the stoichiometry and the volume given to you to actually calculate the molarity. Also, a very common one is you're looking for volume, and volume would be moles divided by molarity. So those are 2 sort of common endings to a solution stoichiometry problem, in addition to the normal ending, where you could kind of do moles to grams using the molar mass as well. So um, those are really the main things that we talked about. Any questions on any of those? All right, we did an example towards the end. Let's do a couple more here just to make sure. So once you give it a go, in a titration, it requires 63.5 milliliters of 0.375 molar calcium hydroxide to reach the equivalence point of 95.5 milliliters of hydrobromic acid. What is the molarity of the hydrobromic acid? So why don't you take a moment there, work through those steps, and see what you come up with. Okay, let's take a look. So again, here we definitely need an equation. So we want to start with the right formula. So calcium hydroxide plus 2 and minus 1 means something like this. Reacts with hydrobromic acid, which is HBr. Remember, an acid and a base going to make basically water from those 2 guys, and a salt from the other guys, as they do a double displacement type of deal here. And that's going to get us here CaBr2. Now that I have the right formulas, I do want to balance them. So I do want to put a 2 there. And I think I will need a 2 there as well to balance it up. Any questions on the equation here? Now that we have the equation, we could really look at sort of what was given to us and really do an analysis of what's going on. For the calcium hydroxide, we have 63.5 milliliters, and we do have the molarity of 0.375. For our HBr, we have 95.5 milliliters, and we are looking for the molarity. So first off, it's definitely not a limiting reagent problem, as we're looking for the other reagent. It is just a basic stoichiometry problem. We can get 2 moles of our calcium hydroxide, and that's going to allow us, when we're looking for our molarity here, to figure out the moles part. The liters part is right here. We just have to do the conversion to liters, and then we'd be good to go to put it in there. So we also need to convert our 63.5 milliliters into liters. So remember that when you are using molarity and volume, you do want to make sure that it is in liters, because that is most likely what you're looking for. 0.0635 liters. Also, big M could get rid of, means 0.375 moles per liter. And we're going to use that as like a conversion factor, just like so that the liters cancel. Liters here will cancel of our calcium hydroxide. And that's going to get us there 0.0635 times 0.375, going to give us a 0.0238 moles of calcium hydroxide. A reminder, we do need to get some moles of our bromic acid, hydrobromic acid, which is where our mole to mole relationship is going to come into play. And from the equation, we can see it is a 1 mole of calcium hydroxide gives us 2 moles of HBr. So we're going to use that as a conversion factor. We'll go 0.0238. We want to get rid of the calcium hydroxide, so we're going to put it on the bottom. Those are going to cancel. That's going to get us here. It looks like 0.04763 moles of HBr. That obviously is the top part there of what we need. So now that we have everything we need, we can put it in there. But first, we still need to convert our milliliters for the HBr into liters. So we'll do our dividing by 1,000. Or you move your decimal place 3 places to the left. Now we have both of the things that we need. So the molarity here would be 0.04763 moles divided by 0.0955 liters. Gonna get us here 0.499, we'll call it. And again, you can leave it as big M if you like, or you can leave it as moles per liter, as both of those units obviously do not cancel out. Any questions on those steps? Again, as we've been talking about a lot, it is the same 4 steps. So that's step number 1. That's really step number 2. That's step number 3 and step number 4. This is also why you should always, and it's expected of you, to write an equation when you're doing these type of problems and not use like the dilution equation like a lot of people sometimes try to do, a little M1 V1 equals M2 V2 action. You will get the wrong answer because the stoichiometry is not 1-to-1. So you do not want to use like the dilution equation here. You do need to work out the steps for the stoichiometry, including the equation and all that kind of stuff. Any questions on that? And I say that because if you sometimes search online, people will give you that equation, M1 V1 equals M2 V2, as like a titration equation, and it works only in a specific type of titration where the relationship is a 1-to-1 between the acid and the base. If it's not, then you will get the wrong answer. So you should never show it that way. Any questions on titration, solution stoichiometry type problems? So next thing we're going to talk about is normality. And normality is another kind of unit of concentration. And when we use normality, normality is really the number of equivalents per liter. There's also something that we sometimes calculate, which is known as equivalent mass, which is grams per equivalent. And what is an equivalent? Well, an equivalent, when we kind of deal with acid and bases, is based on how many H pluses an acid could give, or how many OH minuses a base can actually give. So if something is monoprotic, which means it has just one hydrogen to give, like HCl, it would be for 1 mole of that guy, it will give you 1 equivalent. If something's like diprotic, for example, like H2SO4, for every 1 mole, you'll get 2 equivalents because it has 2 hydrogens that could do as well. So the equivalent weight is the amount of grams per equivalent of an acid or base. And we oftentimes will kind of use equivalent sort of as like a conversion factor to convert between these type of units. So for example, again, if you had something like H2SO4 and 1 mole H2SO4, you would have 2 equivalents. And again, that's because it basically has 2 hydrogens. And again, in like HCl, and 1 mole of HCl, you would have 1 equivalent, again, because it has 1 hydrogen. So, and the same thing as you can see with a base, something like sodium hydroxide would have 1 equivalent of hydroxide. Something like we just used in the last problem, calcium hydroxide, it had 2 hydroxides, and you would have 2 equivalents per something like that. So you could do it with bases as well. A lot of times we do it with acids, but you could also do sort of that with bases. So the equivalent mass is the same thing as it says down here, basically the equivalent weight. And it's kind of like molar mass in a sense, but it might be a little bit different if it is diprotic or triprotic type acid. So as we talked about before, some common strong acids and strong bases are like that HCl, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydriodic acid. Remember that a lot of our strong bases are group 1 and 2, so a little calcium hydroxide, strontium hydroxide, for example, barium hydroxide, and so forth. So as I just mentioned before, again, it really does just sort of come down to sort of like a conversion factor, and it is based on how many H pluses or OH minuses that acid or base could basically deliver to the solution. So let's take a look at one here and see, for example, if we wanted to calculate the equivalent weight of H3ASO4, how would we go about doing it? Well, frankly, we'd go about doing it by just calculating the molar mass. So remember that if we take the molar mass here of H3ASO4, that's going to be 3 times 1.008 for our hydrogens, plus our AS there, which is 74, looks like 92. And 4 times 16 for our oxygens. And this will give us a molar mass like we're normally used to sort of doing of 3 times 1.008 plus 74.92 plus 4 times 16. About 141.9 grams per mole. And that would be our molar mass, but we're looking for our equivalent weight or equivalent mass. So that is where we take a look at our H3ASO4. And when that breaks apart, you get 3 H pluses and ASO4, 3 minus. That means that it is as simple as that. In 1 mole of this guy, we would have how many equivalents? We would have 3 equivalents, right? Because it basically has 3 hydrogens. So we could use that as a conversion factor and go for every mole of our ASH3ASO4. We get 3 equivalents. That means the moles will cancel, and that will get us then an equivalent weight of about 47.31 grams per equivalent in this case. Because it has 3 hydrogens, we can see that the equivalent weight is actually a third, right, of the molar mass in this case. Now, let's just say, for example, we had our HCl. And if we got the molar mass of our HCl, 1.008 grams per mole plus 35.45 grams per mole, going to get us there 3646 grams per mole. In 1 mole of HCl, because it has just 1 hydrogen, you would get 1 equivalent in this case, which means if I took my 36.46 grams per mole and I use my conversion of 1 mole of HCl is 1 equivalent, I will end up with 36.46 grams per equivalent. The equivalent weight and the molar mass in this case are actually the same because it's a 1-to-1 relationship. So it can happen that the molar mass and the equivalent weight will be the same if it is a monoprotic, has 1 hydrogen or really 1 hydroxide, for example, if it's a base to give. Any questions on equivalent weight or equivalent mass? When you used to do titrations like you did, that's what they would have you calculate is like the equivalent mass of your acid and stuff like that. They may still have you do that, maybe at 1A. I don't know if they do that still, but that was a very common experiment. Any questions on that there? So let's talk a little bit about normality. As I mentioned before, normality is actually abbreviated with a big N, kind of like molarity has the big M, but it is equivalents per liter. So it kind of works the same way as what we were just doing. We could figure out how many equivalents there are, for example, of an acid, and we could actually calculate the normality of a solution by really just kind of converting the molarity, for example. If you have the molarity into normality by using the equivalents per liter. So let's take a look at one here. What is the normality of a 2.5 molar sulfuric acid solution? So because it's 2.5 molar sulfuric acid, we know we have 2.5 moles of sulfuric acid per liter. We essentially want to go to equivalents per liter, which means the bottom part's fine. We just really need to change the top part from moles to equivalents in this case. And again, we do it exact same way as we just did. In this case, if we had H2SO4, it's going to break apart into two H pluses and an SO4 2 minus. That means that that gives me a 2 for my equivalents. 1 mole of H2SO4 will give us 2 equivalents. So we could really just kind of approach it more like a conversion factor here. And again, we're going to get rid, in this case, the moles. So we'll put the moles on the bottom. And our equivalents up on top. And this would get us then 2.5 times 2. Give us 5. And the units would not cancel, so it would be equivalents per liter. Or just like molarity, you can just write big N instead, H2SO4. Any questions on that? So I say that's another common unit of concentration. I would say nowadays, usually, that big box we had of base and acid in lab last week. A lot of times from manufacturers, they send it in normality. It's kind of the units that they use, and those kind of ones that come from the manufacturer. I say in most cases for us, and in lab, molarity is again probably more often what you're going to come across. But good thing, I guess, to know. Any questions on normality? You could also, obviously, since normality is a concentration unit, you could do all the types of concentration type calculations that we did before. You could put that into the dilution equation instead of molarity and kind of do a dilution type thing as well with it. You could do all those type of calculations we've done before. All right, I think that should wrap up this chapter. I'm going to say so. All right, 16, which I can go with acid and bases since that's what it says. Sounds like a good one. All right, so this chapter, obviously, we're going to talk about acids and bases, what they are. We'll also talk about pH scale, and we will finish with buffers, I think, which is the topic for our final labs this week, I think. Or one of the topics, I suppose. So let's talk a little bit about acids. Acids were first recognized by their sour taste. A lot of things that we see have acid in them, like vinegar. The main component is acetic acid, which is a weak acid, which is that acid that you used to do a titration with last week. Lemons have citric acid. Bases are characterized by a bitter taste, and they're very slippery. A lot of soaps, drain cleaning solutions are bases. You could go to like Home Depot and buy just straight sodium hydroxide to unclog your drain. Comes with a lot of warnings. Bases are referred to as alkalis, and alkaline, as we might have talked about as well, means basically basic. And that is, again, why we talked about their group 1 and group 2s, where we find a lot of our strong bases come from, which are alkaline metals, right? Our alkaline earth metals. So a lot of bases come from group 1 and group 2 on the periodic table. Sort of an early definition and that was used for acid and bases was one done by Arrhenius. He did a lot of work with electrolytes, which again are solutions that will break apart into ions and conduct electricity. He defined an acid as something that's being able to produce hydrogen ions in solution. Now, when we talk about acid and base chemistry, there's a couple of things. When we talk about an acid, we're talking about the ability of something to produce basically free floating H plus ions in solution. So not attached to anything, just kind of freely floating around in the solution. And if something has the ability to do that, is considered an acid. Now in acid-base chemistry, H plus is known as the hydrogen ion. It is also known as a proton and is known as a proton because hydrogen has one electron, one proton, and no neutrons, which means the only way it can become positively charged is to lose an electron, which leaves it just a proton. The other thing is H3O plus. That is known as the hydronium ion. And for all intents purposes, H plus and H3O plus in acid-base chemistry are the same deal, part of the solution. Anywhere that I write H plus, because I most likely will write H plus, because you could pretty much there H3O plus for it. That goes in equations, that also formulas as well. I would say nowadays books use mainly H3O plus most of the time. So again, anywhere you see H3O plus, pretty much it's the same thing as H plus. And a base is something that has the ability to produce hydroxides. So kind of the same thing as the acid. It is a substance that has the ability to produce free floating hydroxide ions in solution. And as we'll talk about, the amount of H plus ions you have or OH minus ions that you have in solution has an effect obviously on things like pH or whether the solution is going to be acidic, basic, or neutral. So here, if you take some hydrogen chloride gas and dissolve it in water, you get hydrochloric acid. We talked about naming acids when we did nomenclature, so you should know how to name them. Sodium hydroxide as well. And again, in solution, remember that acids do have the aqueous symbol next to them. And that aqueous symbol indicates that it's an acid and not in this case hydrogen chloride gas in the gas state. So again, acid should always have that aqueous symbol, and a reminder that the cation for all acids are pretty much H plus is the cation or the positively charged guy that is there. Now, what is the difference between, I said you could get like H3O plus or H plus is basically the same. For example, if we did write a strong acid like hydrochloric acid, just dissolving in water, we would have an equation like H plus and Cl minus, which is actually, what's happening is basically breaking apart into its ions. Now, you could just as easily write this exact same, and this is what is referred to as a dissociation of an acid in water by including the water. And if we do include the water, what actually happens is the H plus is going to go over there to the water. And if you do, you will get H3O plus and Cl minus. So these two guys are essentially the same thing. And really, it usually depends on whether or not you kind of include water in the equation for just the acid breaking apart in water, basically. So it's a lot of times we'll include the water as part of the reaction that's happening, kind of dissolving HCl in water and allowing it to break apart into its ions. And that's why they will get H3O plus. But it is just as correct to just show the dissociation of it like that, where you'll get H plus. So take home messages, H plus, H3O plus, pretty much the same thing, represents the acidic part of the solution. Any questions on that there? Now, It was a good step, the Uranus equation, but he did a lot of work with bases that actually have hydroxide in them. And not all bases, for example, have hydroxide in them. For example, as we will see, something like ammonia, which is actually a weak base, can react with water. And in this particular case, what happens is the water actually will send an H plus over, and it will make NH4 plus, which is ammonium, and it will make OH minus in this case. And it will be able to produce hydroxide. It doesn't have hydroxide in the formula, but it's able to do a little reaction with water and actually produce hydroxide, which is why it's considered a base. It is why it is also considered a weak base, because something like sodium hydroxide, which if you want to think about it, basically is carrying the hydroxide with it. So when it goes for a swim, it's a strong electrolyte, which will 100% break apart into Na plus and OH minus, and it will be able to produce a lot more hydroxide, for example, into that solution, because all it has to do is go for a swim and it's going to produce hydroxide. Ammonia's got to go find some water, got to do a little reaction to produce the hydroxide. So it's not going to be able to produce as much hydroxide, which is again why this guy is a strong base versus ammonia, which is a weak base. So I would say, typically speaking, your strong bases will have hydroxide in them. And as I mentioned before, kind of that lithium, sodium, potassium hanging right on the periodic table, calcium, strontium, barium, any of those guys with hydroxide will typically be your stronger bases. Any questions on that there? So a more sort of general definition of an acid and base is one that was produced by Bronsted Lowry, and it's the Bronsted Lowry definition of an acid and a base. And in the Bronsted Lowry definition of an acid and a base, an acid is a proton donor. So that is something that will give away an H plus and donate it. And a base is something that is a proton acceptor. So it will accept the H plus. It's really important when you think about this definition and the idea of the H plus, it is not just a hydrogen that is moving. It is something with a positive charge. So the thing that really messes up people a lot of times is you do have to adjust the charge. So if somebody loses an H plus, if you lose something that's positive, you become one more negative. So the overall charge of it changes and becomes one more negative. And obviously, if you gain the H plus, you're gaining something that's positive, which means the charge of that thing will change by becoming one more positive. So it's something that people always sort of forget or kind of mess up on. They know about the hydrogen, but that positive charge is really important because it does affect the charges of things as somebody gives it away and somebody accepts it. For example, as we just saw there a second ago, my NH3 plus my water. Gonna make NH4 plus and OH minus here, right? So in this case, what is happening, the H plus is actually going over here to the NH3. That means that is my base. That means in this case, water is acting as the acid. It is the one that's donating the actual H plus over. When that NH3 gains an H plus, it becomes nitrogen with 4 hydrogens and also becomes positively charged because it gained the positive charge. Our water lost the hydrogen and becomes negatively charged, goes from neutral to one more negative. And by the way, as we will talk about, the process of this creates what are referred to as partners. This on this side here is what is known as the conjugate acid. And this guy is known as the conjugate base. And they are related to the guys on the left-hand side. So our base on the left is related to our conjugate acid on the right. And our acid on the left is related to our conjugate base on the right. These things are both related to each other, as you can see by right there, the 1H plus difference. And that is the only difference that they can have. The relationship between those are really important. And as we will see, your typical straight acids and bases, regular acids and bases, are found on the left-hand side of the arrow. Your conjugate partners, conjugate acids, conjugate bases, are found on the right-hand side of the arrow. So products are typically where you find your conjugate guys, and your regular acid and bases there on the left-hand side of the arrow. So here's a general reaction, what we were just talking about, and the relationship that we see. Once again, acid on the left, which is what that HA is, like anything like HCl, whatever it may be, and our base and our conjugate acid in this case. Now, if you take a look at that equation that I wrote with my hydrochloric acid, and we did write the water into the reaction, in this particular case, the H plus is coming this way. And the HCl here would be our acid. And I'll make what we talked about a second ago. Our water here would actually be our base in this case. This would be our conjugate acid. And that would be our conjugate base. So in this case, the relationship that we see, our HCl is our acid, is related to our conjugate base, and our water, which is our base, is related to our acid. The difference here is just that 1H plus. So as the acid goes from the left-hand side to its conjugate base on the right-hand side, it has one less H plus than it started with. As the base on the left-hand side goes to the conjugate acid, it has one more H plus than it started with. And that again has to be the absolute only difference between an acid and its conjugate base pair. So if you have something that you're asked, like, are these guys pairs, and the difference is more than one H plus, they are not pairs. So it can only be one H plus for them to be pairs in this case. By the way, I just wrote two reactions, right? In one reaction, water acted as an acid, right? And the other reaction, water acted as a base. And there are substances that could do that. They are known as being amphoteric, which something could act as an acid or a base. And water is an example of that. In certain cases, it could act as an acid. And in other cases, it can act like a base. And as we'll talk about, it can even react with itself. And one's acting as an acid and one's acting as a base, as two waters sort of come together and react with each other. Any questions on that there? So as I mentioned before, that again is our only difference. We could only have that one H plus difference for them to be a conjugate acid base pair. Let's take a look at some here and see perhaps. And here's just a drawing of what's going on. Again, donating out. And as I mentioned before, because we do have water in there, we will create that H3O plus, which is our hydronium ion, which again is the same as basically H plus. So this is why, again, hydrochloric acid here is considered an acid. It has that ability, basically just going into water, it's going to produce that H plus. It's really going to release that H plus into the water solution and make free floating H plus or H3O plus. All right, so take a moment for each of these, decide whether or not they are conjugate acid base pairs. Okay, so let's take a look. So hopefully you know what you're looking for is pretty straightforward. You're looking for is basically the difference in H plus. So that's basically the only difference we could have. So we take a look at the first one there. We got HClO4 and ClO4 minus. We look at the difference between these two, it is just an H plus, right? So if you put the H plus on the guy on the right, you get the guy on the left, or if you take the H plus off the guy on the left, you get the guy on the right. So that would be, here we have HCl and ClO minus. The difference here between these two is an H plus, but it is also a oxygen, which is not good. So that is more than just an H plus. So this would not be a pair because obviously one has oxygen and one does not, right? So in this particular case, we take a look here at H2PO4 minus and HPO4 2 minus. The difference here is just one H plus. And again, this is what I was also talking about in terms of the charge. For example, if we take the H plus off of this guy, we end up with HPO4. It was already -1. We lost the positive, so we become one more negative. So that's why it ends up at -2 here. So again, that positive charge is really important as well because it does affect sort of the end product. But in terms of this question, it is a pair. And lastly here, we have HNO3 and NO3 minus. Are these guys pairs? These guys are pairs, yeah. Any questions on that there? How about H2SO4 and SO4 2 minus? Are those pairs? The difference between these is how much? 2 hydrogens. Is that 1 hydrogen? That's not 1 hydrogen. They are not pairs. They are definitely related to each other. They're related to each other from sulfuric acid. And by the way, when something is a diprotic acid or triprotic acid, for example, the hydrogens actually come off one at a time. They don't all just like drop off at once. So what would happen in this case is this guy would lose 1 hydrogen and make HSO4 minus. Then that HSO4 minus would lose 1 more hydrogen and make SO4 2 minus. Yeah. So they actually do come off in what's referred to as a stepwise dissociation. They just all drop off at once. By the way, is it easier, you think, to get off the first hydrogen or the second one? It's actually the first one's much easier because it's neutral, right? As soon as you remove it, you now have something with a negative charge trying to rip off something that's positive. It's going to hold it tighter. So it's actually a lot harder to come off the second one. And if you have something that's a triprotic acid like phosphoric acid, it's actually super hard to get that like third one off. It will come off, but super small amount will come off at that point. That is why if we're looking for pairs, right? Something like SO4 2 minus and this guy, they are pairs, right? The only difference is 1 H plus. Also H2SO4 and HSO4 minus. They are also pairs as well. But going directly from H2SO4 to SO4 2 minus, they are not pairs because again, that's a 2-step process as you go through it. So although they again are related to each other in that sense, they are not related to each other in terms of conjugate acid base pairs. Any questions on that there? All right, so for each of these, why don't you write the conjugate base? So starting with these, what would the formula of the conjugate base be? Okay, so let's take a look. So hopefully at this point, you know that it is an H plus difference. The key on these type of problems is people can't decide should they put it on or take it off, right? In terms of what you should do with that H plus. So those are your 2 options. So this is where understanding where these things come from in terms of conjugate bases and conjugate acids. So if you remember, we had acids on the left and bases on the left, and they go to our conjugate acids and our conjugate bases. And remember that the relationship here is the acid on one side is related to the base on the other. Base on one side is related to the acid on the other. So if you are not sure what you should do, but they did ask you, like they did here, to write the conjugate base, that means you want to end up over here, which means if you think about it backwards, everything that you are looking at is an acid. And all you have to use is the Bronsted Lowry definition of an acid, which is something that will donate an H plus. So now you know all you have to do is take off an H plus in each of these cases, and you will have the right conjugate base. So doing that, we'll remove an H, leave the S, and it was neutral, and we removed an H plus, so it becomes one more positive, one more negative, and it will be HS minus. Same thing on the next one. We're going to remove the hydrogen, so that gives me an S. It's already -1, so it becomes one more negative, which will give me a -2. Here, we're just going to remove a hydrogen. Bless you, gives you NH2. It was neutral, which means it becomes one more negative, so it would be NH2 minus. And lastly, here, we're going to remove one of those hydrogens, get an HSO3 minus. Any questions on any of those? So I say a lot of times they will just ask you to write the formula of the conjugate acid or conjugate base. They won't really tell you what you're dealing with. So you could think about it sort of backwards and figure out what it is. And if it's an acid like we just did there, you take off the H plus, and if it's a base, obviously you would accept it. Any questions on that? So let's take a look at one like our friend here, which is amphoteric. Why don't you write the conjugate base for this one? And why don't you also write the conjugate acid for this one? So it has the ability to go both ways. It's amphoteric. So starting with that guy in the middle for each of them, what would be the conjugate base? What would be the conjugate acid in this case? Okay, so let's take a look. So once again, we'll start with conjugate acid. So same idea. If we're not sure, we want to end up with conjugate acid, which means in this case, our guy is going to act as a base, which means it's going to actually accept the H plus. So he's going to actually kind of bring an H plus in, and that will give us H2CO3, or carbonic acid. Just like we did in this problem, if we were looking for the conjugate base going backwards, that's going to be an acid, which means it's going to donate the H plus, and that will end up at CO3 2 minus our carbonate. Any questions on that? So this is again another amphoteric substance. I would say you come across a lot of amphoteric substances that have this sort of arrangement. It's got a hydrogen and like a negative type charge. A lot of times they could go both ways because obviously they have the hydrogen to give, and they can also accept that H plus as well. Any questions on conjugate acid base pairs here? So a little bit about acid strength. There are obviously strong acids and weak acids. And remember that we can have a weak acid, which is really a weak electrolyte. And by the way, a strong acid or a strong base is also a strong electrolyte. And with weak electrolytes, you remember we have those arrows heading in the opposite directions here, or both ways. And again, there's that kind of forward direction going from reactants to products, and the reverse direction going from products to reactants. And in these type of situations, at some point you'll gain enough products that they will start heading back the other way. The deal here, though, with our weak acids is it is not going to generate anywhere near, for example, the amount of H plus in that solution as something that's a strong acid will. So if the forward direction predominates, we have a strong acid. And again, those guys are going to be 100% ionized or dissociated, which are fancy ways of saying it's going to completely break apart in solution. And again, that is why if we took something like HCl, it will, because it is a strong electrolyte and a strong acid, 100% break apart into these ions. That means when you throw some HCl into a solution, you are generating a lot of free H plus. Also chloride, not going to affect anything in terms of the acidity, but you'll have a lot of free H plus in there. You'll have none of the HCl units still together. They will have completely broken apart. And that's different than in our weak acid situation. For example, HF, which is hydrofluoric acid, is a weak acid. When it goes into a solution, it will break apart into H plus and F minus. The main difference is that is mainly what you're going to have in solution. It's actually going to stay together. It will produce a little bit of these guys on this side. So if you take a look at the beaker, when you put HF into solution, you mainly have HF floating around with a little bit of H plus by itself floating around. And again, it still is able to produce some H plus, which is why it's considered an acid, but it'll produce nowhere near again as much as a strong acid because it's mainly going to stay together because it's a weak electrolyte. So that is the major difference there, and why, again, something like HCl is a much stronger acid because, frankly, all it has to do is go for that swim, and lots of H plus go into the solution very, very quickly, and it increases the amount of H plus in that solution very fast. Any questions on that there? Now, there are some relationships which are, dare I say, important when you get to 1B, I suppose. But the relationship is if you have a strong acid, it will contain a relatively weak conjugate base. And if you have a weak acid, it will contain a relatively strong conjugate base. So if you have basically a strong acid or base, it will have a weak conjugate base or a weak conjugate acid. So what does that mean? It means that essentially those things that it produces, these guys over here, they're really going to not react anymore. They're sometimes considered to be neutral in a sense because they're that partner. Now, if you had something that was a weak acid or base, its conjugate partner is going to be relatively strong. So you would have a strong conjugate base or conjugate acid. Now, when we talk about it being a strong conjugate acid or strong conjugate base, they are still way weaker than a true strong acid or strong base. But really what it means in this sense is these guys that are produced will actually keep reacting. And you may be asking, what will it keep reacting with? It will actually keep reacting with water, which is known as a hydrolysis reaction. And because of that, it will affect the pH. So just to give you an example, and we're not going to really deal too much with this at all. You'll see it again in 1B when you get there. But if we take our guy that we just talked about, which is our hydrofluoric acid, that is a weak acid, which means it will break apart into H plus and F minus. And basically, because this is a weak acid, this will be a relatively strong, again, conjugate base, not a strong base really, but a strong conjugate partner. And what F minus, for example, has the ability to do, because this is obviously, there's HF in the solution, there's H plus and F minus. There's also obviously water floating around in an aqueous solution, because that's what an aqueous solution is made up of. What can happen is actually the F minus can then continue to react with water. And when it continues to react with water, it will actually act as a conjugate base and accept an H plus from water. And it will produce some more HF. But the result of that is it will also produce more hydroxide in that solution. And in that solution, if you had something, say, like a sodium fluoride solution, you would expect it to be more basic because it will actually be able to produce some more free hydroxide in that solution. So that is what is referred to as a hydrolysis reaction, this bottom reaction here. Hydrolysis because it involves water, but outside really the scope of our class. But that's what we mean here when we talk about something being sort of a strong conjugate acid or conjugate base, is those guys have the ability to continue to react. And in the essence of acid, affect the acidity or basicness of a solution or pH of a solution through its reaction. These guys over here, if you took something like hydrochloric acid, which is H plus and Cl minus, this Cl minus, which is the conjugate base, will not continue to react with water. And that's why it's considered neutral. It won't produce any more H plus or H3O plus, for example, or anything like that. Any questions out there? All right, so some are strong acids, which we have our list, and it's really good to know the strong acids. So again, there's our 4 of them, along with hydrobromic acid, hydriodic acid. Those are our strong acids that you should know. And as we talked about before, something like sulfuric acid can donate 2 hydrogens. Again, they come off one at a time. If something has the ability like HCl to give away 1 hydrogen, that is what is referred to as being monoprotic, has 1 hydrogen to give. Something like H2SO4 is known as being diprotic, di meaning 2, protic meaning protons, and something like H3PO4, which is phosphoric acid, is sometimes referred to as being triprotic. So somebody says this is a monoprotic acid, it means it has 1 hydrogen to give. Somebody says it's diprotic acid, it has 2. And if it's a triprotic acid, it will have 3. And again, they do, as we talked about, if there's 2 or 3, come off one at a time, just like we talked about there with sulfuric acid. Any questions on that there? A lot of acids are what are referred to as oxyacids, which means they do contain oxygen. And those are our guys that have those polyatomic ions in it, if you remember. So I think we might have even drew it, if I'm not mistaken. We drew something like nitric acid once upon a time when we were way back when. Like something like that, yeah. So that's nitric acid, HNO3. It is always that OH bond. In this case, with oxyacids, there's going to be what's going to be broken, and that is the hydrogen that basically comes off to make it an acid. A lot of organic acids have a carboxyl group, and the most popular one is the one that we used the other week, which is acetic acid, which is what you find in vinegar. And this right here is an organic group known as the carboxyl group. And it is still this OH, and that is the hydrogen that's going to come off. By the way, none of those hydrogens come off because those are all non-polar. They're hanging on. They're not going to come off. It's just that polar OH group over there that's going to release the hydrogen into the solution. And that's what's going to make it an acid. Any questions on that there? That's acetic acid and nitric acid. All right. So as I mentioned before, there are certain things that can be amphoteric, which means it can act as an acid and base. And those are the 2 examples we saw earlier. We have in one case water acting as the acid, which is the top part here, again, donating the H plus. And in the other case, it's acting as a base, is going to accept the H plus. As I mentioned before, water can even act with itself. It's sometimes referred to as the autoionization of water. One water is the acid and one water is the base. So in this case, that would be my acid. That would be my base. And it will produce H3O plus and OH minus. It will set up what is referred to as an equilibrium. This is a reversible reaction where essentially the water will break apart into H plus and OH minus. And again, H plus, OH minus, same thing here, or H plus and H3O plus, same thing in this particular case. This is an equilibrium type reaction, and we can actually write what is referred to as an equilibrium constant for it, which is an important one when we talk about acid-base chemistry. And let's talk about that. We could write what is sometimes referred to as Kw, and Kw is the ion product of water. I personally will write Kw like this. Kw is equal to the concentration of H plus times the concentration of OH minus. And although it does change with temperature, pretty much 99.9% of the time, you could pretty much use this number, which is 1 times 10 to the minus 14. That is the same equation as what is up here. And again, this is one of the first ones that we will see where H3O plus and H plus can be used, once again, interchangeably. So again, means the same thing here, H plus, H3O plus. Now, there is a really important relationship. And by the way, when we do put these little brackets, which means concentration, we are really talking about molarity in most cases. Moles per liter is basically what we're talking about here. Relationship is as one goes up, as the concentration of H plus increases, the concentration of OH minus decreases. So one goes up, one goes down. They work opposites of each other. So if H plus goes down, OH minus increases. Yeah. We can use Kw to figure out the concentration of H plus or OH minus in the solution if we know the concentration of one of those things. So if we know the H plus concentration, we could calculate the OH minus concentration. If we know the OH minus concentration, we could calculate the H plus concentration. And we could use those concentrations and compare them to determine whether or not equations acidic, basic, or neutral. So if you calculate the H plus concentration and it's larger than the OH minus concentration, that basically means the acid part is bigger than the base part, then the solution will be acidic in that case. If you calculate the OH minus concentration is larger than the H plus concentration, then the base part of the solution is larger than the acid part of the solution, and it will be basic. And if you happen to calculate it that they equal this same number, which means they both will equal 1 times 10 to the minus 7, then you have hit a neutral solution. And that really is the definition of a neutral solution. Each of those concentrations are equal to each other. How do you do the calculation? The good news is it's the same calculation regardless of which one you're given. So whichever one you're given, either the H plus or OH minus, you take 1 times 10 to the minus 14 and you divide it by the concentration that's given to you. And then you simply compare the two concentrations. This is a good reminder and super important in this chapter. Make sure you are still using your exponent buttons. Yeah. If you are not, you're going to find yourself way off in this chapter. Yeah, definitely as we do some more calculations. So make sure that when you punch these things into your calculator, you use that exponent button because you would definitely find yourself way off as we get into some further calculations. Any questions on that there? All right, let's try one here. So for each of these solutions, two separate ones, what is the OH minus concentration? Actually, there's 4 of them. Are the OH minus concentration and are they acidic, basic, or neutral? So see what you come up with. So since we're getting to the end, let's at least take a look at the first one and then you can finish the rest of them. We'll pick up with it next time. So in this case, if we're just looking at the first one here, we're going to be looking for the OH minus concentration. And again, the good news is it's really the same calculation regardless of which one is given to you. So in this case, the OH minus would be Kw divided by H plus. Once again, Kw is really a constant for all intents purposes, and it's always this number, 1 times 10 to the minus 14. And we're going to put our number into here, 3.4 times 10 to the minus 4. Remember, again, using our exponent buttons, so like a 1, exponent button, negative button, 14 divided by 3.4, exponent button, negative 4, and equals, making sure you put it in correctly. That should give you 2.9 times 10 to the minus 11, and this would be molar as it is a concentration, and that would equal our OH minus concentration in this case. Now we do want to compare at this point the H plus concentration, which is the acid part, to the OH minus, which is the base part. Which one's larger? It is the H plus in this case is larger than the OH minus. Also a reminder that when you have a negative exponent, The smaller negative exponent is the larger number because minus 11 means I'm going 11 places that way and putting zeros. Minus 4 means I'm only going 4 places that way and putting zeros. So again, that negative is important here. That means that it would be acidic in this case, the first solution. Yeah. Any questions on that there? Okay. All right, we're laid